All right, so let's do a few more difficult ones. Let's look at number 4. So not every time that we have something to integrate is it going to be a U substitution. Just like when we took derivatives by chain rule, or even regular derivatives, sometimes we did some algebra or used our trig rules first to change what the equation or the derivative, or in this case, the antiderivative, will look like so that we can use a rule that we already know. So in this case, hopefully you'll recall that, didn't mean to do that, the 1 over the cosine is the secant. Therefore, 1 over cosine squared is actually the secant squared. But our angle is 2x, not just x. So the first thing we've done is put this into a different form. We've used our trig identities to put this into secant squared in order to get something that we can do something with. So if you go look at your 6 trig derivative rules, you'll notice that one of the derivatives is the secant squared. So which one is that? So the derivative of tangent is secant squared. So we know that we're going to have an antiderivative of the tangent. However, we do have a function inside a function. We have that 2x nestled inside the secant. So let's call our u 2x. That makes our du 2, but that was a derivative with respect to x. So we're going to rewrite this now as the secant squared of u, secant squared of u. And we have the dx, but we're missing the 2. I'm going to put the 2 in because now 2 dx is our du, and I'm going to balance that with a 1/2. So I'm now going to be integrating 1/2 the integral of the secant squared of u. All right, so my antiderivative in terms of u is constant multiplier of 1/2. The antiderivative of the secant squared is the tangent, so I have the tan of u plus c, that arbitrary constant we were working with before. And then my last step is to turn my fu, my f of u, into f of x. 1/2 tangent of u, which in this case is 2x, plus c. Okay. Let's go to number 5. And don't forget, if I'm going too fast, it's a video. You can pause. Now, if you go look at your 6 trig derivative rules, you'll notice that there is no trig function whose derivative is tan. So I don't get to just go backwards and say the antiderivative of tan is something. So just like in our last question where we had to rewrite using a trig identity, we're going to do the same thing here. Hopefully you remember that tangent is the same thing as sine over cosine. So I can rewrite the tangent of x, or the integral of the tan x, as the integral of sine x over cosine x. Now, I have 2 functions now. I have a sine x being multiplied to a 1 over cosine. Or I have sine x being divided by cosine. So out of the 2 functions, sine and cosine, one of those is going to be my u. Now, when I'm choosing my u, remember, let's go back to the rules. I'm looking for the one that's most nestled. What's inside? Or what's harder to get to? What can't I just directly get to? Sine of x is just a multiplier. I can directly get to sine, it's just sine of x times stuff. What's trickier to get to is a denominator. So the cosine, or a denominator, we're going to look at that as if it's nestled because it's tucked in under that fraction bar. So let's always make a rule that for the most part, 99.9% of the time, if we have a denominator, it's our u. Okay, now I need the derivative of u. Now, what gets tricky for kids with U-substitution, or anybody, adults too, is we're anti-differentiating in this problem. We're anti-differentiating sine over cosine. But to do an anti-differentiation problem with U-substitution, there comes a point where we are differentiating. So even though I want to do the antiderivative, I need to take a derivative. So if my u is cosine, I'm now taking the derivative of cosine, which is negative sine. And once again, I'm going to chain on that derivative, that was a derivative with respect to x. All right, I'm now looking to rewrite my sine over cosine dx using all of u and all of du. So cosine of x is in the denominator. So that means I have 1 over the cosine of x. 1 divided by the cosine of x. Okay, that's used. Now I am looking for negative sine x cosine x. I have positive sine x cosine x. So the only thing I'm missing is a negative 1. If I put in negative 1 to give me my du, I have to multiply by what will balance negative 1, so that I'm in the end only multiplying by positive 1. So negative 1 times another negative 1 is positive 1. All right, all of this now is my du. So I have the integral of 1 over u times du with that negative 1 hanging on out in front. Okay, let me write that as u, 1 over u du. Okay, I've used all of du, all of u, and now my job is to take the antiderivative. So this is why I started our topic on the last video with this integral. What antiderivative is 1 over u du? Well, remember where we started the last video. If I take a derivative of the ln of u, I get 1 over u times du. Oh, wow. 1 over u du, 1 over u du. That means my integral of 1 over u du is ln u, multiplied by the constant multiplier of negative 1. So my antiderivative in terms of u is negative ln u plus c. And then putting that back in terms of x, I get negative ln u, go back and plug in u, it was cosine of x plus c. So it's weird, yep. my antiderivative is negative the ln of the cosine of x plus c. All right, this one, sorry, it went down to the next line. Let's cross that out. Okay, we want to evaluate the antiderivative of all of this squared times x plus 1. So we have three functions here. We have the base of the quadratic, x squared plus 2x minus 3. We have the power function, that base is being squared. And then we're multiplying by a third function, or a third expression, x plus 1. Out of those three, the one that's inside, the one that's most nestled, is the one that is the base to the power of 2. So let's call that our u. Following the pattern we've been doing, I'm now going to find the derivative of that u. 2x plus 2 dx. Now, I want to put this all in terms of u and du. I can see I have u squared, and now I'm trying to find 2x plus 2 dx. Well, I don't exactly have that, but maybe I've noticed I have a GCF of 2 here. So if I factor out the 2, I'm left with x plus 1 dx. Oh, x plus 1 dx. X plus 1 dx. The only thing missing from my du is a 2. So I'm going to put in the 2 to make my du and compensate by also multiplying by a half. I am now taking the antiderivative of 1/2 the integral of u squared, and everything else was du. So my antiderivative, constant multiplier of a half, keep the base, add 1 to the exponent, divide by the new exponent, or multiply by the reciprocal, plus c. And now simplifying and putting u back in, I have 1/6 u, which is x squared plus 2x minus 3, which is cubed, plus c.